now it's on, so I'm going to re-say that again. 4.3 to 4.4 is on exponential and log functions. Okay? We're going to start with exponential, and then we're going to move into logs. They are inverses of each other. Exponential functions take on the form f of x is equal to some number a, where a has a positive real number. A also has to be greater than 0 and not equal to 1. Its domain is all real numbers, and it takes on the form f of x equals a to the x power. These are laws of exponents that can apply, and those will be helpful in your challenge problems, obviously, just kind of manipulating different things, taking the product, taking the sum, things like that. So let's go ahead and graph our first f of x function, the most common one, in fact, I think for exponential, when the base is 2. So when I'm graphing this, there are 3 key points that we like to graph all the time. Anyone tell me the x values of those 3 points? You use your context clues. Negative 1, 0, and 1, right. So in the x, I'm going to go ahead and write negative 1, 0, and 1. We're going to plot those 3 points first. Okay? When I plug in negative 1, I do 2 to the negative 1 power. Because of the negative exponent, it takes the reciprocal of my base, so that's equal to 1/2. When I raise anything to the 0 power, it's always equal to 1, and something raised to the first power is itself, the base. So I'm going to graph those 3 points, where this is my x-axis, this is my y-axis, 0, 1, negative 1, 1/2, and 1, 2. It might not be easy to tell which way the function kind of curves, but this is a straight line, even though it might look at it from graphing these 3 points. When I put in 2, 2 squared is really 4, 1, 2, 3, 4, so I'm going to plot a couple extra points here. When I plug in 3, 2 to the third power is 8, 2, 3, 4, 5, 6, 7, 8. So as I move to the right, as x increases, y exponentially increases. Okay. So it gets really big really fast. As I go to positive infinity for x, I go to positive infinity for y. It doesn't get vertical. I want everyone to understand that. It does keep increasing over here, but it gets really big really fast. On the other side, as I go towards negative infinity, I plug in like negative 2, negative 3, negative 4, negative 10. When I raise anything to the negative power, it takes the reciprocal, but it makes the power positive, so that ends up still being a positive number. So, since the base can never be non-negative, this never goes below the x-axis. It gets infinitely close, but never touches the x-axis. So where the domain is all reals, the range is restricted by that horizontal asymptote, I guess you would call it. So, rather than me saying all that, obviously this information kind of sums it all up for you. Okay, you can read through that at your own leisure. Make sure that makes sense, understandable. Obviously, we can generalize this and make not just 2, but any base value, right? 3, 4, 5, 1/4, 1/10. And then this would always be true, and it kind of helps you find those values quickly. It's a smooth, continuous curve, no corners or gaps. Fun. Go ahead and graph that one. Again, if I ever pause, go ahead and just try it on your own. Pause the video, try it yourself, see how it goes. Yes. If I'm raising 1/2 to the negative power, I take the reciprocal of the base, that makes it 2, 1, and 1/2 respectively. Graphing those points. Bless you. I end up with a graph that kind of looks like this. So if I overlay the 2 graphs from the previous problem and this problem, you don't have to do this, but kind of just to give you an idea of what we're talking about here. I get something that looks like it's reflected over which axis? The y-axis, right? Reflected over the y-axis. Which should make sense because remember, when we take the independent variable, we make it negative. The exponent, if we make it negative, it's like we're flipping over the y-axis. Okay? What happens if I make the base negative? Well, I can't have it negative, but if I had like a negative out in front of it, like y equals negative 2 to the x power, what happens then? flips down below the x-axis, right? So that's the big difference we have to worry about there. Remember, anything added or subtracted to the x value in the exponent, what's going to happen for that one? Transformations here. If I add or subtract something to the x, take a guess. Do it with your hands. Left and right, right? Okay? But if I add or subtract something outside the exponent to the base, add something or subtract something here, I'm going to shift it up or down. All these transformations are very common. We've seen them before. It's just kind of in a new form. So here we have the same type of exponential function, but here where a is between 0 and 1, meaning a is a fraction, these properties are true. This is a fun little fact. I'll add this to our things to remember for calculus. E is a number. It's not a variable. Don't let that fool you. Future tests or quizzes. E is never a variable. It's always a number. And it's defined using this expression. 1 plus 1 over n, that sum raised to the n power. Now, it's not just that value at n. It's as n approaches positive infinity. As I make n very, very large. Give me a large number. Something you can wrap your brain around. Large number you can wrap your brain around. It's not a trick question. Just any number. That's too big. 420? Yeah. Interesting. All right. 420. So, when I plug that in, 1 plus 1 over 420, all raised to the 420 power. All right. Now, in my calculator, in my head, 1 over 420, what's that going to be equal to? Almost 0, right? Basically really small. And that, something really small plus 1, is something that's a little bit greater than what? This is small. 1 plus something really small is what? Bigger than 1, right? A little bit bigger than 1. And then that raised to a really big number is going to be what? Is it going to increase or decrease? Increase, because it's greater than 1, right? But because it's such a small value off of 1, it's actually approaching some value called e. And e is an actual number, irrational number that they were able to figure out. And this idea of a limit, we're going to come back to this next quarter and talk about that. The limit as a value approaches infinity. Cool. So, exponential equations, the equations that involve terms in the form of a to the x power. You can solve them using your law of exponent properties, which you saw on the first page. Also remember, if a to the x power is equal to a to the y power, then I can set the exponents equal to each other, as long as they have the same base. The same base. So when I look at letter A here, to solve this equation for x, it'd be great if my bases were the same, but right now one base is 3 and one base is 27. It'd be great if I could change 27 into a different base. How would I write 27 as an exponent? Maggie? 3 to the third power. 27 is equal to 3 to the third power. So now, since the bases are the same, I can set the exponents equal to each other. X plus 2 is going to be equal to 3, meaning x is equal to 1. X equaling 1 is the only value that makes that equation true. Go ahead and try B. Give it a shot on your own, then we'll kind of walk through it together. Does everybody see the difference between e to the x squared power versus e to the x to the third power? What's the biggest difference? What's the obvious difference? The parentheses, right. And the parentheses show me that I'm doing a power to a power. And if I'm doing a power to a power, what's really happening between that 3 and the x? We're multiplying, not raising it to a power. So don't treat this as 3 to the x to the third power. It can really be rewritten as e to the 3x power. Any ideas of what I should do with this whole fraction going on over there? Yeah, I can use that reciprocal property, right? 1 over something to the positive power is really like that base to the negative power. If I take the product of two different, at the same base, what am I doing with the exponents? Adding. or in this case, I guess subtract it. E to the x squared is equal to e to the 3x minus 2. Any ideas I should do now? Since I made it look like a to the x is equal to a to the y. Yeah, they're exponents equal to each other. So now, x squared is equal to 3x minus 2. A little square rooting, right? Square root, and we'll divide by 3. Now, what do I got to do? Yeah, we're all doing it, but we got to factor. Bring everything over to the left. Bring everything to the left and go from there. Two numbers that multiply 2, but subtract to negative 3, or add to negative 3. My solutions are 2 and 1. 2 and 1 respectively. Fun problem, man. Fun problem. Oh yeah. Any questions about that? Alright. Exponent equations. Good stuff. Now, we said in the first page, though, that exponent functions, because their domain is all reals, and because I can switch the x and y values, they are one-to-one functions. They pass the horizontal and the vertical line test. Every exponential function does. So since that's true, I know it has to be a one-to-one function, and its inverse is called a logarithmic function. Strauss is one of Strauss's struggling words. Logarithmic. Nope, did it again. Screwed up. Logarithmic. Yep, the more I say it, the worse it gets. Log. You'll hear me call it a log function a lot, because that's just easier for me. Got to think about the word specific very carefully. Specific. So, a log function is the inverse. It's written in this form where the base a, okay, and it's defined, this is a really helpful point right here, y is equal to log base a of x if and only if, a biconditional statement, x is equal to a raised to the y power. Okay? That relationship is very important. Because it's biconditional, it works both ways. I can go from exponent to log and log to exponent very quickly. The domain of a logarithmic function is 0 to infinity, which is the range of the exponential function. And vice versa, the range of the log function is the domain of the exponential function. So where I had a horizontal asymptote, now I have a vertical asymptote. So change each exponential function into log form. So here, since this is my base of 4, that's my base of my log. So when I get this value here, I'm going to get 3 is equal to log base 4 of a. Now you might not be as quick with it as I am there. So what I actually do, every time, I'm going to rewrite b here. When I see b to the third equals 27, in my head, I'm kind of taking the log base b of both sides, the log base b of both sides. And if I take the log base b of that same base, they kind of cancel out. And what can I do with that exponent? I can bring it down in front. So this 3 can come down in front and become a product of that. Log base b of b is 1. So 3 is equal to the log base b of 27. Okay? In my head, that's how that kind of goes. Rather than looking back at that biconditional statement and trying to pull it out of there, I come up with a little trick to kind of help me remember how that works using my log properties. E to the x power equals 1. So here, that means I want to do the log base e of 1, and that should be equal to x, right? Is there another way to write log base e? Yeah, ln. So you can see it in this form, and that's correct. Or you could also write it as the natural log of that same base. Lowercase n, lowercase l, another way to kind of write log base e. Rewrite each log in the exponential form and solve for x. So here, right now I'm in log base form, but I want to rewrite it exponentially and then try to find its value. So, kind of working backwards, right? If this is my base, then that's the base of my new exponents. X is really going to be equal to 3 to the 4th power. So, log base 3 of x is equal to 4, which means 3 to the 4th power is, what is it? 81, yeah. Good old 81. Log base 5 of 125. A lot of you can put that in your calculator. You have a log base kind of thing you can change, but without a calculator, it's easier to visualize this as an exponential function rather than as a log function. So if that's my base, that means I'm really doing 5 to the sum x power is equal to 125. How many times do I need to multiply 5 to itself until I get 125, basically? 3 times. 5 times 5 is 25, multiply by another 5, and I get 125. Negative 1 is equal to log base x of 6. So let's go ahead and take the x to the negative 1 power is equal to 6. What value can I plug in there for x? Or when I raise it to the negative 1 power, I get 6. 1/6. It's a reciprocal. So x had to be equal to 1/6. For a lot of you, it's easier to go from log to exponent and kind of solve it from there rather than vice versa. Now remember, once we change from log to exponent form, we can still use that property of the fact that the two bases are equal, then their exponents are equal. So let's find the exact value of each of these logs. Okay? We could put this in our calculator, but if we don't have our calculator, we have to be able to kind of switch it back to exponent and solve. So we want to find the value, the exact value of when the log base 2 of 32 is equal to something, right? X, let's call it. So I want to solve for x. So to do that, I'm going to have to raise x to what power, or what's the base if x is going to be my power? 2, because it's the base of my log. So 32 is really equal to 2 to the x power. So I got to think of my powers of 2, which if you're in the program, it's a big one. Powers of 2, right? 2, 4, 8, 32, right? So 2, 4, 8, so that's 2 to the 4th power? No. Yes? 3rd. What? 5th. 5th. What did I miss? 8, 16. Missed the 16. Also, it's really helpful in, I think, measurements. Like inches. If you look at a ruler next time. 1/8, 1/16, 1/32, 1/32. If it was a dentist world, that's what it would be. Log base 5 of 1 over 125. So if I raise this to the 5th power, call it y now. 5th power of y, y to the 5 to the y power is equal to 1 over 125. Yeah. -3, right. Let's kind of use this property, though, just to make sure we understand it. 125, how could I write that as a base of 5? 5 to the 3rd, right? So this is like 1 over 5 to the 3rd, which really would kind of be like this. Right? If you want to work backwards a little bit. Rather than trying to figure out what value of 32 goes 2 to what power gives you 32, change 32 into a bunch of 2's. To graph the log function, remember that its inverse is exponential. Let's go ahead and graph this function. It's going to reflect across the line y equals x. Any idea how we should do that? Yeah.
You have to start plugging numbers into y first.
Yeah? So we got an xy chart. What y values do you want to plug in? What are the ones we really like? Or what are the x values we liked in the exponential functions? -1, 0, and 1, right? Since those were the x values we liked in the exponential function, for the inverse, let's flip it across. For y, let's put in -1, 0, and 1. And we'll see what we get out when we plug those in. Remember, if I would make this exponential function to be 2 to the y power is equal to x. So when I put in a -1 here for y, what do I get out for x? 1/2. When I plug in 0, I get 1, and when I plug in 1, I get 2. So really, all we've done with these points, which are kind of our critical points, or points to remember for exponential and log functions, is that they kind of just get flipped across the x and y values. At -1/2, I'm at -1. At 1, I'm 0. And at 2, I'm 1. Now remember, the line y equals x is my kind of reflecting line for inverses. So let's kind of sketch that out. It's a wavy line there, Mr. Ausel. And if I graph the original inverse function, get something that looks like that. And obviously with our beautiful red and orange and black, we get two functions that are inverse of each other. Because these are inverse of each other, a lot of their properties are going to be similar between logs and exponents, but they're just kind of flipped around. The domain and range is kind of flipped from exponents. I have an x-intercept where I don't have a y-intercept. For logs, that was switched around for exponential functions. The y-axis is my vertical asymptote, and so on and so forth. It's a smooth, continuous curve with no gaps or corners. These are some tricky questions here, jumping in with domain. But the domain of an exponential function goes from 0 to infinity, meaning that x's have to be what in the domain? They have to be greater than 0. They have to be greater than 0. It's 0 to infinity. So they have to be greater, not equal to, but greater than. So what I want to do in my independent variable, which is inside the parentheses here, I need to figure out whatever value is in my parentheses here, that value has to be greater than 0. X plus 4 is what I'm taking the log base 2 of. So that value, x plus 4, has to be greater than 0 for this log function to exist. It's got to be. So remember, when you add subtract the inside, what happens to the graph? Shift which way? So in this case, to the left, since we're adding 4, it's the left or right shift. Adding outside the parentheses would shift me up or down. So here, this is going to be x has to be greater than -4, meaning that my domain in set notation would be from -4 to infinity. Or in interval notation, I should fix that. Interval notation, it's got to be from -4 to infinity. Three for a loop here for b, a rational function. Without graphing, let's kind of discuss here what would cause domain restrictions here or issues in this graph. What are some values that would be a problem for this function in letter b? The value of +2, right? When I plug in x equals +2, I get a 0 in the denominator, which can't exist. So obviously x cannot be equal to -2. Or +2, I should say. +2. What else happens? What other issue do I have in terms of a point? What's wrong with -1? The entire rational function, if I put in -1, that becomes negative, which is a problem because it has to be greater than 0. Is that it? Just negative 1? Negative 2 is a problem too, right? Because that makes the top 0. But you can't be equal to 0. It has to be greater than 0. So I can't be negative 1. I can't be negative 2. I can't be 0. When I plug in 0 for x, what do I get inside parentheses? Negative 1. That's no good. So it's got to be greater than positive 2, right? How about positive 1? Nope, still negative, right? 1.5? Nope, still no good. So it's got to be, x's have to be greater than 2. Now, can I ever get too far negative? We said there's a problem at negative 2, right? What happens at negative 3? It's positive again. Which is a very strange thing for logs because you're not used to looking for the second part. But eventually, if I make it a big enough negative, it makes both of the numerator and denominator negative, which then makes a negative divided by a negative really positive. So x's could be greater than 2 or what? Less than negative 2. So I could write it like that in inequality notation, or I could look at it like this: negative infinity to negative 2, and then 2 to infinity. If you're not quite trusting of me in our class math, you can always pull out your graphing calculator, graph it, right? You just got to be careful. You got to look at the first and fourth quadrants of your graph because something's going to appear down the fourth quadrant that you're not going to expect. Tricky there with the rational functions. Got to be careful. We do have some special log functions here. Obviously, whenever I write a log with no base, if the base is not written, you can assume that the base is 10. Base is 10. So whenever there's no base, you can just it's understood that it must be 10. Natural logs. Obviously, we already talked about this, log base e. That's going to be the natural log, only if that is true. So here we have some calculator questions. Go ahead and grab your calculator. So the first problem they ask us in our notes to do is log 8. So technically this has a base of, no log was indicated, so I can use just log of 8, right? And because the calculator just assumes that there's no base, then it means that the base is 10, that would be an acceptable answer, 0.903. But let's say they change the base to like 5, right? If they change the base, this is how you would do a change of base in your calculator. You would go math, I can't remember. I go so far down, I want to go up, if that makes sense. Over there to A, log base, which is in your calculator maybe, depending on your operating system, or whatever you have loaded up. Log base lets you put in a value for the base, which is kind of sweet. So if I wanted to do like log base 5 of 8, I could do that if I wanted to. Man, you'd think you cut the base in half, it would be double the size. It's not. It's weird things about logs. Alright. Any questions? Alright, so this was, we said was 0.903. Who's got letter B there for me? Log of 1/5. Negative 0.699. And natural log, just to make sure we understand, natural log is right below log. Natural log of 5. You don't have to include that ending parenthesis if you don't want to, but just be careful. 1.609. Fun stuff. 3 decimal places. Unless you're told different. Use transformations in the graph to graph the following function. Determine the domain range and vertical asymptote of the graph. Actually, it's funny. The last thing they tell you to do is probably the first thing that I always do. where would that vertical, on the parent function, on a log function, where's the vertical asymptote located on the parent function? On the y-axis, right. So originally I was on the y-axis, but I added a 1. I added 1 to the independent variable, which you would think plus means right, but really it means 1 to the left. So really I'm going to move this vertical asymptote from the y-axis to -1. X equals -1. Now, I'm not trying to trick you out here. I'm just going to go ahead and graph the original parent function just so we can remember where we started from. The original parent function kind of looks like that. That's the original parent function. Log of x, right? But here, oh no, wait, this is log base 10, isn't it? You guys didn't catch me. Log base 10, right? So this isn't going to be 1/10 and 10, right? So here, it's not based off the 2 system, it's going to be based off of when I take the log base 10 of x, it's really going to go, it's still going to have 1, 0, but then when I plug in, I'm going to go up to 10, it gets big fast. Yes. Yes. Holy smokes. Alright. Pretty sure this is a 10 by 10 graph. No, it's not. Of course it's not. Use it for theory. Yeah, right? Just like right here. Ish. Sure. Alright. Because, if it was a 10 by 10, that would make more sense. Alright. So, there's my original parent function, but here, we're going to multiply the outside by 2. How's that going to change the overall value? So let's look at the original XY chart. We had, at -1, I would have been at 1/10. At 0, I would have been 1. And at 1, I would have been at 10. Or at x equals 10, I would have been at 1. Okay? Now, since this is being multiplied by 2, first of all, let's shift these points a little bit, right? This guy is going to be shifted over 1. This guy is going to be shifted over 1. And this guy is now 10. So really, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9, so he's like right here. So, those were the points after I shifted him. But, now I'm going to multiply it by 2. So, when I multiply it by 2, what's going to happen to those values? What's going to happen to -1 and 1? Here. Since I'm going to change, think about it. I'm multiplying the entire outside the log function by 2, right? Since I'm multiplying it by 2, what's going to happen, what's not going to change is not the x values, because that's on the inside. What's going to change is these y values, because I'm multiplying the log function by 2. So when I multiply -1 by 2, what do I end up at? -2. So here, -1 really goes down to -2. The origin, or that value at 0, what's 0 times 2? 0, okay. And then what's 1 times 2? So here, 1 is going to pop up to 2. Oh, dang, son. So if that 2 was a negative 1, or no, if it was not negative, it was a fraction. Rather than stretching it, it would shrink it. Okay? I see some questions. Go ahead, ask them. Are you okay? The black graph here is the original parent function. So this needs to be shifted and then stretched. You okay with that? No? Yes? Okay. All right. All right. Toughie. Transformation practice to come. Because the shift, you're right.
Oh, because of
the shift would have taken it from these. This would really become 9. This would really become 0. This is causing, this plus 1? Yes. So the points were off, but the graph is right. 1/10 really became what? When I took away 1 from it. 1/10 minus 1. Negative 9/10. Yeah, negative 9/10. So everybody okay with the blue values changing because of the plus 1? And the negative 2 changes the y values to stretch? Not by adding 1 or subtracting 1, just by multiplying it by a scalar too. Alright. Cool. So, the actual algebra part. It's my bread and butter. I don't know. Part that I always liked. If there could be more algebra and geometry, it'd be my thing. Alright, so the first thing you want to do when you're solving a log equation, you want to isolate the log, you want to convert it to exponent form, and then solve the exponent equation and check for extraneous solutions. Okay? So, solving this equation. The first thing I want to do is I want to go ahead and isolate the log. Is there only one log right now? Yes, right? We're not expanding or contracting logs yet, but if I could, I would need to do that as such. But right now, he's got 1 log. So, if I want to turn this into exponent form, I would raise this to the 4th power, meaning 2x minus 1 would really be equal to 4 to the 3rd power. And 4 to the 3rd power, we all know, is 64. So 2x minus 1 is equal to 64. So when I add 1, I get 65. And when I divide by 2, x equals 65 halves, since 65 is not divisible by 2. Or, what is this in decimal? 30 what? 32.5. Letter B, log base x of 81 is equal to 2. Again, we don't think in logs, we think much easier in exponents. So first thing I'm going to do is, once the log is isolated like it is, then I'm going to go ahead and turn it into exponent form. So this means 81 is really equal to x to the 2nd power. And to solve that, what do I have to do? Take the square root. And I think I heard the magic word there. When I introduce the square root, what do I have to worry about? Plus or minus. So plus or minus 9 equals x. This is where the last step comes into play. Technically, mathematically, I have to include the plus or minus because I introduced the square root into the problem. However, I need to check for extraneous solutions. Okay? Why can't I have a negative 9 as my value for x? Any reason why?
It would be negative, so negative 9 squared, but it would be, the negative would not be equal to 9. So it would be 9 squared.
What? If I would plug that back in, right, to the original log function,
Yeah.
I'm pretty sure my base of my log can't be negative. Let me check that. Let's go pull up the old calculator there. Let's just check to make sure. Math, log base. Oh, dang. Don't do that. Don't do that. Log base of negative 9 of 81. Maybe I'll be blown away and it will work. Oh, non-real answer. Non-real answer. So I plugged in the negative value, okay? It doesn't work. Meaning, and it makes sense, right? I think when we talk about exponents, the base of the exponent or the base of the log has to be non-negative. So, here, negative 9 can't be one of my solutions. That's one of my extraneous solutions. Extraneous. So, x is really equal to only positive 9. Extraneous. Solving for exponents using logs. So, change to a log expression, solve for the variable, and use the calculator to approximate the value. Right now, why can't I solve this in exponent form? That's always things. We forget that sometimes. Why can't I solve this in terms of exponents? Yes?
Because one is base E, one is base 6.
One is base E, one is base 6. And right now, based on what we know, we can't turn those into the same base in exponent form. Okay? But I can convert it into a log form. Okay? So I've isolated the exponent expression, but I'm going to change them into logs now. So I need to get the that 3x out of the exponent. Any recommendations on what base I should choose for my log? If I want to get x out of the exponent, I want to get x by itself. What base am I going to choose? It's not a variable, it's a number. It's e, right? E. E is no good. E, I want to get rid of that. So if I take the natural log of e to the 3x power, and what I do to one side, I have to do to the other. Right? Natural log of 6. When I take the natural log of e, the exponent can be brought down as a scalar. Or a scalar multiple. Not scalar per se, but it can be brought down as a multiple. Multiplier. Factor. So, ln to the e power, ln of e is really just 1. So 3x is really equal to the ln of 6, or the natural log of 6. To solve for x, I divide by 3, right? And my final answer would be x is equal to the natural log of 6 divided by 3, which, for all our purposes, that's the exact value, and we would need to use our calculator to approximate the actual value of that. Natural log 6. Wait, what? Let's quit. Divided by 3. 0.597. Oh, good old problem. I think we already did this one, didn't we? Yeah. Let's see if you can try it again. Without looking at your notes. Without Mr. Ausel helping you. Go ahead and try example 13. Use those properties. Solve. Your homework is listed below here. You have one challenge problem here between 4.3 and 4.4. It's number 62. And remember the problems, the challenge problems are due on the 11th and 12th, depending on your A day or B day, respectively.